And what was your specialization for your graduate studies?
I collected data with my supervisor from a satellite that is no longer operational, the International Ultraviolet Explorer satellite. It was launched in 78, and I had data from it 6 months later. Actually went to NASA in Washington, D.C., Greenbelt, Maryland, in particular, to actually observe on that satellite, which was a really neat experience. And so I was looking for the signature of the element boron in stars. Boron is a light element that might have been produced in very small quantities at the Big Bang. Hydrogen, helium, and a dash of lithium. But there's theories out there that talk about beryllium and boron, the next lightest elements, being formed at really, really small levels. And we went looking for signs of boron in a variety of stars. And so I was doing spectroscopy in the ultraviolet region of the electromagnetic spectrum, looking for signs of the element boron, trying to put thresholds on how much boron was, or well, how much boron was present in these stars.
And
And how do you
okay.
differentiate between boron that originated from the Big Bang and boron that's being created now?
Boron isn't created now. That's the point.
Oh, oh,
Oh.
oh,
So if you find it, it's primordial.
okay.
Ah. So
So
what
Well,
were your findings from that? Like, did you find like a certain threshold for boron, or did you find what you were looking for?
the threshold, I guess the answer is we didn't find what we were looking for because there was no significant quantity above threshold levels. I don't remember what the threshold level was that we determined, but basically we could not find evidence down to the level of resolution that the IUE satellite was delivering us. We could not find evidence of boron in these stars. So there was a threshold that we could put. Don't remember what that was now. That was like 40 years ago, guys. But that's what we were looking for: signs of boron in these stars. And we were looking across a variety of differing stars so that we could differentiate between the more long-lived stars versus the more recent stellar populations. Couldn't find the stuff, but it was nonetheless interesting to look at the spectrum because we found lots of other stuff in there which we commented upon. But boron itself, no, we were unsuccessful in finding any significant quantity in those stars.
yeah, and let me know if this is just like a quick answer, but what is it about boron that makes it a primordial element?
Basically, because, well, yeah, the short answer is hydrogen, helium, lithium, beryllium, and boron are the simplest elements, and there's no naturally occurring process in stellar nucleosynthesis that generates those particular elements. Let me rephrase that. Hydrogen converts into helium, of course, but there is no stellar nucleosynthesis process that generates lithium, beryllium, or boron. And to the best of my knowledge, there is no process at the supernova end or the merger of neutron stars, black holes, and so on that generates light elements down there. So there's no known, unless something has popped up in the last 40 years, and I must admit I haven't been keeping tabs of it, but to the best of my knowledge, there's no known process that can generate lithium, beryllium, or boron. So the only stuff now we can create it in humanity. We can create those elements. However, naturally occurring sources, no.
Ah. So when you deal with like your variable star research, because I mean we haven't actually got into like the research that you conduct right now, right? Like because you're a kind of variable star astronomer.
Mm-hmm.
Does does any of this knowledge from like your graduate school like come into like play? Like have you ever done something in your graduate or undergrad which you use to this very day in your observational variable star research?
One of the things that I did while I was doing my master's degree, studying spectra and looking for boron, is that I was also working with one of the other professors in the department looking at eclipsing binary star systems. So they are not what we call intrinsically variable, they are extrinsic. That is to say, because of their continuous eclipse processes, they are changing their overall light output. So it's similar to intrinsic variable stars where they're sort of pulsating as a result of nuclear stellar processes. for the 3 summers that I was in Victoria, was a research assistant, and we looked at these binary star systems every clear night that was possible during the course of the year at the campus observatory. We also used the spectroscopic capability of the Dominion Astrophysical Observatory to measure the radial velocity of some of these stars. Bottom line to it is, I was knee deep in variable star research right from the get-go, even though my primary thesis was associated with spectroscopy and looking for boron, but sort of 50% of my time was spent, pretty close to 50%, looking at collecting the data for the other types of variable stars, these binary star systems, and analyzing that data. And in fact, I ended up with more papers out of that work than I did out of boron. That's just the way it worked out in this particular case. So variable stars became a part of my life as a master student. The fact that I'm looking at intrinsic variable stars, stars that are very similar to Cepheid variables, SX Phoenicia stars, that's just happening to be the branch, if you will, that I ended up developing most at York. I didn't come to York with the plan, we're going to do SX Phoenicia stars. I came to York doing a variety of different things, including just training undergraduates and graduate students on data collection processes. But it worked out that SX Phoenicia stars have got all the right attributes to observe on a university campus anywhere on the planet. And so we adopted that project, and we continue to observe every clear night, looking at a subset of those stars to this day.